Okay, in this section, we're being introduced really to radical expressions and exponents. So let's take a look. So what we're going to be able to do is multiply radicals, divide radicals, add them, subtract them, perform all the operations that we can with radical expressions, and then we'll also learn about their exponent properties as well. So we'll start basic here in chapter 8.6a. So what we've seen before is that 5 and negative 5 are the square roots of 25, because 5 squared gives me 25, and negative 5 squared also gives me 25. So just quickly then, the square roots of 49, well, 7 squared gives me 49, but negative 7 squared also gives me 49. So that means 7 and negative 7 are the square roots of 49. The nth root of a real number a can be written as the radical expression nth square root of a, where n is what we call the index. So n is the index. And that's something that you're going to want to be comfortable with saying, is your n is your index. N is your root of the radical, and a is the radicand. Note, if the radical sign has no index, so it looks like square root a, it represents a square root. So it's understood that there is a 2 out there. We don't typically write the 2. It's understood that this is a square root. So here are some real quick examples. 2 squared is 4. So the 2 is the square root of 4, because 2 squared is 4. 2 cubed is 8, because 2 is the cube root of 8. 2 to the 4th is 16, so 2 is the 4th root of 16. And we could keep on going on this list forever if we wanted to. When a number has more than one real root, the radical sign indicates only the principal root or the positive root. So the radical sign is always going to indicate a positive root. I'll show you in just a moment that there are cases where you can have more than just the principal root. And we'll see that in just a minute. But let's get some practice here, rewriting the radicand so that you have the exponent that matches the index. So what does that mean? Let's take a look at an example. So it says square root of x to the 4th. Remember, if there's not a number there, it implies that there's really a 2. We want these two to match. So we want this really to say x squared. The only way we could do that is to say x to the 4th equals x to some number times my index. So 2 is my index. What number times 2 gives me 4? In this case, it's 2. So I can rewrite this as the square root of x squared to the power of 2. And why does this help? Why are we doing this? The reason is that this 2 and the square root, sorry, my pen's bad. Give me a minute. Let me go get a new pen. All right. So the reason why we're doing this is that this 2 and the square root, they cancel each other out. Squares and square roots undo each other. So we always want to make this power here match the index. Here the index was 2. So those cancel off, so we're left with x to the power of 2. Let's look at one that isn't a square root. Let's look at a cubed root. So the cube root of x to the 6. We could do the same game. X to the 6 equals x to some number times the index. Well, what's our index? It's 3. So it's some number times 3. So what times 3 gives me 6? In this case, this is going to be x to the 2 times 3, because 2 times 3 is 6. And the way we would rewrite this is x squared to the power of 3. Now, this power and my index are the same. So this is the cube root of x squared cubed. So what's going to happen? We can cancel off the cube root and the 3, and we would be left with x to the power of 2. So that's how you would go about simplifying underneath the radical. There are, if you There are some shortcuts to doing this, but this is a nice, sure way of simplifying underneath the square root when your power inside is greater than the power outside, and they're easily divisible by each other. Like 6 is easily divisible by 3, 4 is easily divisible by 2. If they're not easily divisible, that's a special case, and we'll look at that later on. But for now, we're going to work with them being easily divisible. So the next part are those 3 cases, or those 4 cases that I was talking to you about. Said you get, depending on your index, that will tell you how many roots you should possibly have. So if you have an odd index, you should have a total of 1 real root. So here's your example. The third root, this is the way they'll ask it, of 8. So what is the third root of 8? So we have third root. Third root means my index, so this gives me a value of my index, is 3. So the cube root of 8 is notated like this, cube root, and 8 is the radicand. So the cube root of 8, and if you do that on your calculator, or using a little bit of intuition, the cube root of 8 is just going to be 2. 2 times 2 is 4, times 2 again is 8. So 2 times 2 times 2 gives me 8. An even index with a positive radicand. So that means the number underneath the radical is positive. You would get 2 real roots. So what would those real roots be? So you would, let's take a look. Fourth root, let's say the fourth root of 16. So remember, the fourth root tells me that's my index, and the 16 is my radicand. So some number times itself 4 times gives me 16. That number, again, if we use a little bit of logic here, is going to be 2. So I would get 2 times 2 is 4, times 2 is 8, times 2 again is 16. So what you get is the principal root right away, you get 2, but when it's an even index, you get positive and negative. So you need the plus or the minus sign when your index is even and your radicand is positive. If your index is even and your radicand is positive, you get 0 real roots. So your example here, let's say the fourth root, oops, that says roof. Fourth root of negative 16. Again, this is a fourth root, so that means my index is 4, and underneath the my radical there, or my radicand, sorry, is negative 16. Well, that would give me an imaginary number. That would give me plus or minus 2i. So we're just going to say, in this algebra 2, we're just going to say that this is imaginary. And we're going to leave that as our answer. There is no way I can take the square root or the fourth root or the sixth root of a negative number. We're just going to call it imaginary. We're going to leave it alone. And this is only true for even index. When it's odd, you can take the cube root of a negative number. You can take any odd index and take the root of that negative number. You only don't get a real answer if your index is even. A radicand of 0 has 1 root of 0. So if I have the third root of 0, well, this is third root, so 3, and my radicand is 0, is just 0. Okay, so here's some examples. So the fourth root of 81. So fourth root means my index is 4. So this means I have 4, and inside my, underneath my radical is 81. My radical is 81. So if you do that in a calculator, the 3 times 3 times 3 times 3 gives me 81. So I would have 3. But remember, I told you, your calculator is only going to give you the principal or the positive root when your index is even. So 4 is an even number, which means I need to have plus 3 and minus 3. Those are the fourth roots of 81. So you need the plus and the minus, since 4 is even. Find the cube root of negative 125. So again, cube root, so that's going to be the third root of negative 125. And if you put that in your calculator, you are going to get an answer. This is going to be negative 5. So 5 times 5, or sorry, negative 5 times negative 5 is 25, and 25 times negative 5 is negative 125. So it is possible to get a negative answer here when your index is odd. Number 3, find the sixth root of negative 729. And I would hope at this point you would say, I see a sixth root, so I'm just going to stop here and say imaginary. And we're not going to worry too much about finding those imaginary roots. This would be plus or minus 3i if you really wanted to. But don't worry about it. You could just say imaginary or no real roots. Either answer will work for that one. Multiplying and dividing roots. So we're going to take a look at the product property. The product property says that the nth root of a times b is equal to the nth root of a times the nth root of b. So I'll give you 2 examples of this one. The first one will be the cube root of 16. The cube root of 16, we want to try to break up 16 into some number that's a cube times a number that's not a cube. So the easiest way to do this one is the cube root of 8 times 2. And you could get that from the chart that we filled out in class of the cube numbers. So 8 is a cube number. So I can break this apart as the cube root of 8 times the cube root of 2. And certainly we can do the cube root of 8. That's just 2. We can't do the cube root of 2, so we're just going to be cube root of 2. So that would be our answer. 2 cube root of 2. This is also true for the case where you have numbers and letters mixed together. So if we could squeeze one more in here, that would be great. Let's say we have the square root of 4x to the power of 2. Well, I know I can break this apart using this product property. So this is going to be the square root of 4 times the square root of x squared. Well, I know the square root of 4. The square root of 4 is 2. And just by inspection, here I have a power of 2. And remember, in a radical, without a number, it's implied that there's a 2. So these would cancel off, and I would be left with 2x. So the square root of 4x squared becomes 2x. So that's the product property. The quotient property, very similar, except now you're dealing with division. The nth root of a divided by b is equal to the nth root of a divided by the nth root of b. So here's your example for that one. Your example for that one, the square root of 25 over 16. Again, this is a square root, and we can break it apart according to the product property as a square root of 25 over the square root of 16. Square root should be pretty easy to recognize. The square root of 25 is 5, and the square root of 16 is 4. So 5 over 4, and you could leave your answer like that. So here's one where they're asking you to multiply 2 radicals together. As long as the indexes are the same, you can multiply radicals together. You just got to check and make sure the indexes are the same. And in this case, is that true? Are the indexes the same? That would be yes. They're both square roots here. So I can do the square root of 2x times the square root of 6. That would be the square root of 2x times 6. And we could simplify this is the square root of 12x, because 2 times 6 is 12. And you would get to this point and you would say, well, 12x is my answer. But this is not fully simplified. We want to see if we can rewrite 12 as a perfect square times some number that's not a perfect square. Or sorry, a square number times some number that's not a square number. So if I'm going through the list of the square numbers, I know that 12 is the same as 4 times 3, and then I would have my x. So I just broke apart 12 to be 4 times 3. And now I can rewrite this as a square root of 4, since this is all multiplication, times the square root of 3x. Square root of 4, we know that, that's just 2. The square root of 3x. 3 isn't a perfect square, and the exponent on x is 1, that's less than 2. So this is just going to be 2 square root of 3x. There's no way I can simplify the square root of 3x. Example 2. Simplify the square root of x squared over 49. So again, we're going to use our quotient rule. So the quotient rule says that the square root of x squared over 49, we can rewrite it as the square root of x squared over the square root of 49. The square root of x squared, well, notice I have a square and I have a square root. Those cancel off, so I'm left with x. And the square root of 49 is just 7. So x divided by 7. I will do the part on rationalizing the denominator and the part on adding and subtracting radical expressions in the next video.